the success and rapid development of deep learning in the past decade, its applications have had reach into the realm of control theory and search algorithms in the form of deep reinforcement learning. While deep reinforcement learning is showing promising results, it is still in its researching phase. We will be looking at research papers published in relatively recent years and attempting to interpret what the paper's contribution may mean in the grand scheme of artificial intelligence and control systems. I will be commenting on each papers and presenting my own opinion on them and their possible ramifications on the field of deep reinforcement learning and its future. In this video, we will first be covering papers in fields known as imitation learning and multitask learning. We will then cover an influential paper called Diversity is All You Need, which resides within the field that serves as an extension of multitask learning, hierarchical reinforcement learning. Papers that have cited diversity is all you need reach into other fields as well, mainly model-based reinforcement learning and meta-learning, so we will be covering those as well. In order to gain more understanding into the papers in discussion, it is advisable to have preliminary knowledge regarding basic concepts of deep reinforcement learning, mainly policy gradient theorem and actor-critic algorithms. If you are not familiar with these terms and concepts, I've made a video covering such topics called Overview of Reinforcement Learning for you to watch before delving into the main topics for this video. Let's say that we have a dataset that depicts how a certain object moves, like motion capture data of a person performing various tasks such as walking, running, and jumping. And we want a policy depicted by a deep neural network to imitate that movement. The subfield of reinforcement learning that tackles this problem is known as imitation learning, where, in order to train the policy, we attempt to minimize the deviations of its trajectories to those seen in the data that we are trying to replicate. One of the most influential methods of imitation learning is deep mimic, where a convolutional neural network inputs the current state of a character, such as the angles and angular velocities of joints, and the task to be executed, and outputs the angles in which we would want joints to be in, which we will call target joint angles. A classical controller called the PD controller, based on the target angles and the current joint angles, produces actions that attempt to reduce the error between the two values. Although this algorithm is capable of producing results with high accuracy, there are several issues. The paper states that it takes several days per task to train the neural network, which would be a huge problem if the character and motion tracking performer need to perform many tasks. It is also reported to have low responsiveness to user input, which would be a huge inconvenience in applications such as game development. In addition, Deep Mimic, due to its algorithm's over-reliance on the output of PD control, has difficulties responding to small perturbations that may occur during physics simulation. The first paper that we will discuss attempts to build on top of this algorithm and solve some of the shortcomings presented in Deep Mimic. DReCon, Data-Driven Responsive Control of Physics-Based Characters, is a paper by Kevin Bergamin and other authors from Ubisoft and McGill University published at ACM Transgraph in 2019. Taking the fact that Ubisoft is involved in this research into consideration, we can expect a method heavily geared towards application into the game development pipeline. Given that deep reinforcement learning is rarely used for developing game AI and character animations due to the unpredictability of the sequences of outputs produced by deep neural networks, it would be interesting to see how they tackle this problem. We first used the motion capture data to approximate a physical model that best fit the physics depicted in the data. This is accomplished by taking all vertices available in the motion capture data and fitting a character rig within the physics engine composed of cylinders using a method called CMAES, a type of evolutionary algorithm. It is important to note that the physics of the motion capture data is not directly approximated by mimicking its trajectories, but rather by using the provided preliminary settings of the motion capture suit itself. In this case, the number of vertices embedded in the suit and their positions. Due to this indirect approach, we can automatically assume that there is a possibility of having huge discrepancies between the physics of the motion capture and the physics of the approximated model. Then what is the result of this process? The paper states that the resulting character, while still imperfect, provides more realistic mass distributions for each bone and has relatively constant density when accounting for intersections, compared to a character constructed by hand. Just by looking at the first step of DReCon, right off the bat, we can see how Ubisoft takes the methods available in the imitation reinforcement learning field and modifies it in order to alter and automate parts of the game development pipeline. Usually, the computer graphics modeling team first creates a character, and only then does the team working on motion capture data steps in. However, that would mean that it would take extra painstaking effort to modify the character model so that its movement will look natural even when the motion capture data is applied to it. But this method flips the pipeline on its head and said, let's just automatically generate a simplified model and work out the character model from there. In order to capture the state of the generated model, we define a feature vector composed of positions and orientations of joints and center of masses. These vectors are gathered beforehand from motion capture data to form a feature database. During training, the current state, referred to as query vector in this paper, is compared with every feature vectors in the database, and the feature vector with the minimum squared loss is selected. Later on, the distance between these two vectors are calculated and will act as a reference error for a PD control. In my observation, this process strongly reminisces of the Kohonen's self-organizing map, a neural network clustering algorithm where neurons are defined with a weight vector with the same dimension as the input vector and are assigned to its neighboring neurons. In this algorithm, the input vector is compared with the weight vector of each neuron via the minimum squared loss, and the neuron with the lowest loss is selected, just like how the feature vector from the database is selected in the method mentioned in the paper. However, it is important to note that there is a key difference between self-organizing maps and feature vector selection. During the training process of the self-organizing map, the weight vectors of the neurons neighboring the selected neuron are updated to close the distance between it and the input vector. This allows neurons with the similar weight vectors to be clustered together as neighbors. Now that the query vector and the selected feature vector are properly defined, we can now use the PD controller for the physical character to make the transition from the current state as seen in the query vector to the desired state as seen in the feature vector. We will now refer to the difference between the two vectors as the reference error. PD controller, which stands for proportional derivative controller, is composed of two components, a proportional controller and a derivative controller. The proportional controller weighs the reference error with a scalar value. On the other hand, the derivative controller weighs the change rate of the reference error with a scalar value. In this case, this refers to the difference between the reference error of the current time step and that of the previous time step. The sum of these two components is the output of the PD controller. Afterwards, the method in this paper performs a feedback correction, where a neural network trained with proximal policy gradient, a reinforcement algorithm, is used to stabilize the movement produced by the PD controller via feedback correction. The reward function for proximal policy gradient is designed so the output of the PD controller matches the actual output for the physical model. Looking at the individual components necessary to build a reward function, it is evident that the following list of positions and velocities are taken into consideration for matching. Positions and velocities of arbitrary points on the mesh of the physical model, body pose defined by angles of each joints of the model, velocity of the center of mass of the entire body, and the vertical position of the head. Combining all these components, we obtain the reward function. RT equals EFall, parentheses, RP plus RV plus R local plus RV center of mass. I found it interesting how the authors of this paper combined classical control theory and modern machine learning control in order to construct this method. In the control engineering industry, it is widely known that although deep learning may be a hot topic, engineers prefer to use classical control such as PD control or PID control over deep neural networks, since the implementation of PID control is simpler and the movements generated by this control is more predictable than the black box that is deep neural networks. Hence the phrase, slap a PID on it. Let us take, for example, a PD control and alter the coefficients for both proportional and derivative components. For both cases, as the reference is set to a constant value, the state affected by the control output converges to a reference in a trajectory resembling a sinusoidal function. However, it is difficult for this controller to adapt to unpredictable, unknown, or unstable systems. On the other hand, it is difficult to analyze or predict the output of a deep neural network, trained or untrained, without sampling many times over the entire state space. However, neural networks, especially when trained with gradient descent algorithms, can be extremely effective in extracting features from unknown systems and producing outputs accordingly. I find that in the field of deep reinforcement learning, the majority of methods presented in papers merely string multiple neural networks together, either hierarchically or adversarially, and ignore their predictabilities or the amount of insight they give into the dynamic of the system in question. The papers that we will discuss later in this video are some of those examples. Unpredictable control systems can be a huge safety hazard in applications, and if errors were to be found, black boxes are difficult to debug, since each weight values are of little meaning to outright meaningless without the context of the entire network. Additionally, training and testing deep neural networks can be computationally expensive, and oftentimes, the test environments seen in papers have alternative solutions in classical control or optimal control, which are able to complete the task with less complicated control systems, and often either take the environment's dynamics into consideration or give insight into them. For example, there are many reinforcement learning papers that propose methods to learn bipedal locomotion, while in reality, simpler architectures, mainly controlled by forms of central pattern generators, have been proposed for decades. The DReCon utilizes both these methods and lets deep neural networks deal with unpredictable and unknown state dynamics while maintaining predictability using PD control. Perhaps it would be more useful and applicable if more methods utilize both of these control theories and help the industry integrate the advantages of deep neural networks into their projects. Finally, we look at the main results for the response time of the method proposed in the paper. The response of DReCon of user inputs, to quote the paper, is similar to the response of the kinematic motion, and thus similar to the actual time required by the motion capture actor. And compared to other previous works such as Peng's Deep Mimic, the response time of DReCon is significantly shorter. As we can see in the table presented by the paper, given the task of turning 90 degrees, DReCon is able to complete it with nearly half the speed of Deep Mimic. If you want to learn more about DReCon, 2-Minute Papers have released a video also summarizing the experiments regarding this method and the results. Ubisoft themselves have also released a video presenting the overview of the method and actual footages of the character moving according to the player input. Or you could just read the original paper in its entirety. Differential policy gradient was proposed in a thesis written in 2018 for the International Institute of Information Technology, Hyderabad. We will be taking a look at a section of the work, Multitask Reinforcement Learning for Shared Action Spaces in Robotic Systems, that discusses the architecture of differential policy gradient. Figure 3.1 from the thesis shows an overview of the proposed architecture. The overall workflow of actor and critic calculations should resemble that of ordinary actor-critic algorithms. The actor-critic algorithm that the proposed method builds upon is Deep Deterministic Policy Gradient, DDPG, which instead of outputting a probability distribution for the actions, it outputs a continuous vector that represents the actor vector itself. However, you may also notice that the output for the actor is separated into multiple actions, and the output of the critic is also separated into multiple return estimations. In fact, each of these individual actions correspond to each of the rewards and returns that the critic utilizes for training. These are referred to as compound actions and compound rewards, respectively. The compound actions are composed of disjoint and shared actions. The disjointed actions can be interpreted as actions whose reward functions are independent from each other, and the shared actions are actions whose reward functions have similarities or features that act as common baseline. As mentioned in the thesis, the disjointed actions and shared actions are combined to get a compound action. It is important to keep in mind that, as mentioned before, all of these disjoint and shared actions have their own critic function that determine the expected return for each of these actions. Taking a look at the objective function presented in the thesis, we can see that for every disjoint, shared, compound actions, there are separate Q functions assigned to them, resulting in a combination of 3 equations derived via policy gradient theorems. For k disjoint actions dependent on the shared actions, k shared actions, and n minus k disjoint actions independent from the shared actions. The details regarding the derivation of this differential policy gradient theorem is available in the thesis. By having this multi-action approach, or as we will later refer to as multitask approach, it is possible for agents trained with such reinforcement learning algorithms to perform tasks that require usage of multiple limbs, where each limb is required to complete a task unique to its limb. The thesis tests this method via application onto a humanoid robot. The humanoid robot's task is to perform inverse kinematics problems onto different positions around the agent using both arms. The reward function is defined by stability analysis via zero moment point, which measures the momentum of the end effectors of limbs when they reach the goal point, and interlimb collision avoidance. This method's performance is compared to that of the robot trained with DDPG. In the result of the experiment, the humanoid robot trained with differential policy gradient was able to multitask and have each limb perform different inverse kinematic operations at the same time. To quote the thesis, the author found that DDPG is generally unstable for solving multitask problems. In some runs, it may learn initially, but suffers degradations later, and it is observed that the DiGrad algorithm yields better final results while having greater stability. During the commentary of the previous paper, we discussed how deep neural networks can be problematic due to their black box structure, resulting in the difficulty in debugging the model and its unpredictability when faced with unknown environments, and that there are often solutions based on classical control that are both easier to implement and take less computational time for calculation. It seems that this thesis, on the other hand, highlights the shortcomings of solutions based on classical control and possibilities of deep reinforcement learning, at least in the field of robotics. Classical control methods for inverse kinematics problems, such as utilizing the pseudo-inverse of the Jacobian matrix of the system, have existed for decades. However, there are major issues with such methods, such as the possibility of causing self-collision between limbs of the same robot. On the other hand, methods based on deep reinforcement learning are able to overcome this by giving developers an option to manually add a penalty if self-collision were to occur. Additionally, as shown in this thesis, multitasking using multiple limbs are possible using deep reinforcement learning. In the following papers, we will be looking at a more complicated form of generating multitask action distributions called hierarchical reinforcement learning. Specifically, diversity is all you need and its derivative methods. But before we dive into the specifics of the diversity is all you need algorithm, we have to have an understanding of entropy. Entropy in the field of information theory refers to the randomness of a probability distribution. For any distribution, the more chance of obtaining varying stochastic variable when sampled from, the higher the entropy is. For example, a distribution where some variables have higher probability of getting sampled, or in other words, the distribution has deviation towards certain variables, is expected to have low entropy, while on the other hand, with something like a uniform distribution, since it is equally likely for any of the variables to be sampled, it is expected to have a high entropy. Entropy can also be interpreted as the expected amount of information in a distribution. In order to understand this interpretation, let us attempt to calculate the amount of information necessary to store one value, which, in the case of binary memories seen in Neumann-type computers, can be translated to the amount of bits necessary to store a value. If we set this amount to x, the value p can be described as p equals 2 to the power of x, meaning that it takes x binary digits to store p. Digit p can be described as log base 2p. If we swap this value p with the probability p of x of a stochastic variable x, we obtain log base 2 p of x. We can generalize the base to turn this equation into a natural logarithm as standard in mathematics. Additionally, a negative sign is added in order to define the entropy as a positive value. Finally, this negative natural logarithm is weighed with its probability, and obtaining the sum for all the stochastic variables result in the mathematical definition of entropy of a probabilistic distribution. Using the concept of entropy, it is possible to calculate the information loss that occurs while a stochastic variable is transferred from one probability distribution to another. which, in the case of this slide, would be from P of x to Q of x. This loss is referred to as KL divergence. The thought process for understanding the formula for KL divergence is to first realize that there is an underlying assumption that every stochastic variable present in Q of x are also present in P of x. We first want to define the entropy of P of x for all variables in Q of x. This is called cross entropy. We then want to subtract the amount of entropy for the same variables, but for within Q of x. This is merely the entropy of Q of x. Having went through this thought process, we can understand that the KL divergence is defined by subtracting the cross entropy with the entropy. Note that it would mean that, depending on the order of distributions inputted into the KL divergence function, the resulting value would differ, even if the selected distributions for the calculation are the same. Mutual information refers to the amount of information shared between two probability distributions. Defining the formula for mutual information is simple when we think of entropies of probability distributions as Venn diagrams, where the cross-section of the two entropies is the mutual information. Finally, the amount of information shared within a graphical model is known as multivariate information. Multivariate information can be estimated by adding the mutual information between a variable and all of its conditional variables for all variables within the graphical model. An example of such element of mutual information can be seen in an excerpt of the Markov decision process below, where the mutual information between the current state and its two conditional variables, the current action and the previous state, is expressed. In order to calculate the multivariate information for the entire Markov decision process, it is necessary to calculate the summation of such mutual information for all states present in the trajectory. Given the preliminary knowledge regarding entropy, KL divergence, and mutual information, we can finally delve into the diversity is all you need paper itself. Diversity is all you need. Learning skills without a reward function is a paper by Benjamin Eisenbach, Sergey Levine, and other authors from UC Berkeley Artificial Intelligence Research Lab, published at iClear in 2019. Diversity is all you need is a type of hierarchical reinforcement learning, a subfield of reinforcement learning that attempts to combat the difficulties of making the policy learn to navigate through complex environments and tasks, such as having bipedal robots perform forward locomotion in an environment with hurdles, where computationally expensive training processes, such as learning complex trajectories, is necessary. Hierarchical reinforcement learning reinterprets such complex trajectories by separating the trajectory into several simpler tasks called primitives or sub-policies, where each sub-policy is usually depicted as separate policies. For example, if we are training an agent to move forward on a terrain with a hurdle in its way, hierarchical reinforcement learning reinterprets the trajectory necessary to complete the task as a combination of tasks for moving forward, jumping, and regaining stability after the jump. Additionally, a neural network called manager is defined and is responsible for sequentially selecting which sub-policy to execute for every time step k, which in this example would be sub-policies for moving forward, jumping, regaining stability, and back to moving forward in that order. However, in order for the hierarchical reinforcement learning architecture to adapt to multiple and more complex tasks, it is necessary for the manager to have sub-policies that are responsible for completing diverse tasks. In this paper, these various tasks are referred to as skills. One important thing to note before discussing skill task diversification is that diversity is all you need compresses the various potential sub-policies into one neural network, which we will now refer to as skill policy, which instead of inputting the state of the environment, it also inputs what is referred to as skill vectors. These skill vectors determine the skill in which the skill policy executes. For example, if skill vector z0 is inserted into the skill policy, it may execute forward locomotion, while if skill vector z1 is inserted, it may execute the jumping task. In order for the skill policy to have such functionality, it is necessary to design a objective function that rewards task diversification. In diversity is all you need, high task diversification is equivalent to maximizing the mutual information between state and skill, and minimizing the mutual information between action and skill given the state, where the skill gives more meaning on the effect that it has on the environment rather than the individual action sequences themselves. For example, if the skill in question represents forward locomotion, it would be more intuitive to have the resulting trajectory affect the agent's forward position rather than follow a certain set of actions regardless of the agent's environment. Additionally, the objective function attempts to maximize the entropy of the action distribution given the state. This term of the equation refers to the maximum entropy policy, where the entropy of the action distribution is deliberately increased in order to increase the chance of policy exploration. The mutual information term of the objective function can be rewritten using just the entropy, and using the definition of entropy, these terms can be rewritten as expected values of natural logarithms. We have three notable terms: maximum entropy policy, latency estimation, and conjugate prior for skill distribution. For the latency estimation term, since we cannot analytically calculate the logarithm of p of z given the s, we use a separate neural network classifier called the discriminator that predicts the skill that the policy executed given the state. The conjugate prior term is set to uniform distribution. So if the number of skills is n, this term would be 1 over n. The conjugate prior term additionally acts as a baseline for the latency estimation term, since the probability of the selected skill should always be higher than the uniform distribution. When diversity is all you need, the skill vectors are sampled from a categorical distribution as one-hot vectors, which is a vector composed of zeros except for one of the elements, which act as a flag or indicator of classification. Such skill vector are to be inserted with the current state into the skill policy to produce sub-policy actions corresponding to the one-hot skill vector. Is a diagram of the same mechanism where the interaction between environment and skill policy is highlighted. During the training process, a skill vector is sampled from a uniform categorical distribution and is inserted into the skill policy alongside the current environment state. The skill policy outputs an action, which causes the state to change. A separate neural network called the discriminator inputs this altered state and outputs a skill probability distribution. This distribution and the original sampled skill vector are used to train the discriminator to correctly predict the skill vector. At the same time, by using the distribution outputted by the discriminator, the reward function logarithm q phi of z given st plus 1 minus logarithm p of z is calculated, where q phi of z given st plus 1 is the discriminator's output, and p of z, as mentioned before, is the number of skills or the dimension of the skill vector over 1. Using this reward function, the skill policy is trained using soft actor critic, an actor critic algorithm that incorporates maximum entropy policy. Note that the skill policy and the discriminator are trained cooperatively at the same time per training iteration. Now that the skill policy is trained, a task-specific manager function can be trained. For every few time steps, the manager, given the current environment states, outputs a skill vector to be fed into the skill policy. The sequence of the outputted skill vector should result in generating a trajectory that attempts to maximize the return for specific tasks. Since this is a task-specific meta-policy, the reward function is also task-specific. On a side note, members of a lab that I used to be part of and I have implemented Diversity is All You Need around a year ago, whose GitHub repository has been open source since then. The link will be in the description. Here are some of the results when trained with 10-dimensional skill vector on OpenAI Gym environment by Peter Walker, version 2. Diversity is All You Need succeeded in sampling one-hot vectors from discrete distributions in order to train the sub-policy to conduct diverse skills. However, there were still other areas to be explored and experimented. One of the writers in their GitHub implementation of this algorithm proposed an open question. What if we could train such sub-policies using continuous vectors sampled from continuous distributions? It reads, in preliminary experiments, we tried using a continuous prior distribution, P of z. Neither a uniform nor Gaussian prior distribution allowed us to learn skills, as well as a categorical prior. Can continuous priors be made to work? One initial idea is to use a Dirichlet distribution as the prior, as a Dirichlet can interpolate between a categorical distribution, which we know works, and a uniform distribution, which doesn't work yet. The idea of sampling continuous vectors instead of one-hot vectors seemed to have advantages, mainly the lack of the need to preliminarily determine the dimension of the skill distribution and vectors. For example, with Diversity is All You Need, for learning in some environments and tasks, such as walking across the landscape with one hurdle, it may only require 3 skills to accomplish the given tasks. Thus, the dimension of the distribution shall be 3. While learning in more complicated environments may require more than 3 dimensions, and in some cases such hyperparameter may be difficult to determine beforehand. By utilizing continuous skill spaces such as those from uniform or Dirichlet distributions, it may be possible to classify such diverse skills regardless of the number of dimensions. However, problems arise with such ideas and application. In order for the skill policy and discriminator to properly train to classify diverse skills, it is necessary to sample skill vectors throughout the entire skill space, which, since continuous distributions are used for sampling, would result in theoretically infinite number of possible points to be selected. Directly training the skill policy via continuous skill vectors is essentially equivalent to attempting to learn infinite number of skills per policy in the given environment, which is an unrealistic method in application. The next paper that we will cover overcomes this problem by utilizing model-based reinforcement learning. Dynamics-aware unsupervised discovery of skills is a paper written by Archit Sharma, Jisheng Gu, Sergey Levine, and others in Google Brain, published in iClear 2020. As mentioned before, the method proposed in this paper utilizes model-based reinforcement learning. Therefore, we will quickly summarize its concept and explore that skill discovery can be incorporated into it. Model-based reinforcement learning consists of the policy and the planner, or the dynamics model. The planner, given the current state in action, learns to predict the next state as accurately as possible, which enables it to recursively predict the future states and actions trajectory. This enables the agent to estimate entire trajectories for multiple actions given the current state and estimate returns for each of these trajectories. which then the policy can reference to choose a better sequence of actions. The planner's functionalities can be reinterpreted as learning the Markov decision process that consists of sequences of actions and states. Therefore, we will be looking at figures and equations from that paper that visualizes such graphical models. The main difference between MDPs for reinforcement learning algorithms with single neural network and skill searching algorithms, such as diversity is all you need, is that it is necessary for an additional variable, skill, to also be taken into consideration. The joint probability P for the entire trajectory made of states, actions, and skills are as below. The initial state and the selected skill act as conjugate prior to the state transition function and the policy. As we have explored before in diversity is all you need, in order to have diversity in skill distributions, the mutual information between state and skill distributions should be maximized, and the mutual information between action and skill distributions should be minimized. The diagram on the left is a graphical model when these two conditions are optimized. The joint distribution of this model Q is similar to the previous model, except the policy is missing, and the skill distribution is directly influencing the state distribution. Of course, it is impossible to directly influence the state. It must be altered via another distribution. In this case, the action distribution outputted from the policy. So the problem at hand is to find model Q that minimizes the difference between joint distributions P and Q, or in other words, minimizes the KL divergence between P and Q. This is where the reward function for DADS is built upon. DADS utilizes an estimation of minimization of KL divergence via calculating the difference of multivariate information between both distributions, originally proposed in Friedman's and other work in 2001. The calculation of both multivariate information are shown below. After much calculation, the reward function can be expressed as above, where Q represents the estimator for skill dynamics, P represents the state transition function planner, pi represents the policy, and beta represents the Lagrangian multiplier. The gradient of the reward function by the planner reduces the function to one term, the planner. We now look at the training process for DADS. The skill dynamics given a skill vector sampled from a prior distribution and the current state predicts the next state. This network not only serves the purpose within the model-based planning, but also as the latent discriminator as seen in DADS. The policy takes the sample skill and the current state to produce an action that affects the environment, causing the state transition. These two neural networks are trained concurrently. The planner acts as a meta-controller for outputting a sequence of skill vectors to be fed into the skill dynamics function. A separate reward function for training this meta-controller is necessary. For the experimentation of DADS, the paper defines three types of model-based reinforcement learning classifications based on how the planner is trained, where random MBRL utilizes trajectories generated by a randomized policy. Weak Oracle MBRL utilizes trajectories generated by a policy trained on an arbitrary reward function, and strong Oracle MBRL utilizes trajectories generated by a policy trained with the same reward function as that used during the testing process. In terms of how generalized the planner is, random MBRL should fit into arbitrary policies regardless of whether they are trained on a reward function or not. DADS, trained and tested in many OpenAI environments and tasks, perform better than all of the three generic types of model-based reinforcement learning methods. Even compared to diversity is all you need, it performs better. To directly quote the paper, an RL-trained meta-controller manager is unable to compose primitives learned by diversity is all you need to navigate AMP to a goal, while it succeeds to do so using the primitives learned by DADs. DADs have successfully managed to organize skills acquired from continuous distributions. By looking at the skill space not merely as a probability distribution, but also as a dynamics whose transitions should be modeled by a neural network. As the next step of development of diverse skill-acquiring reinforcement learning algorithms, the next paper attempts to reduce the number of neural networks required to monitor the skill space from 3 seen in DADs as the planner, skill dynamics, and policy to just one, the policy, which, instead of inputting both the skill vector and the current state, only inputs the current state, just like a non-hierarchical reinforcement learning policy. This allows the simplification of training due to the reduction of dimensions in the input vector of the policy. It also serves as a generalization of all acquirable skills given the agent, which would remove the requirement of a manager. Unsupervised meta-learning for reinforcement learning is an archived preprint published in 2020 by Gupta, Benjamin Eisenbach, Sergey Levine, and others from UC Berkeley, Carnegie Mellon, and Stanford University. The paper discusses about a framework that combines skill discovery and a field of reinforcement learning, known as meta-reinforcement learning. Meta-reinforcement learning, usually described as learning to learn, learns a policy that is generalized on various environments and tasks that can be converged to an optimal policy when given a specific task or environment in a few gradient steps. One of the most influential methods proposed in this field is model-agnostic meta-learning, or MAML. During the learning process of the generalized meta-policy, a dataset containing a variety of environments and tasks, such as a variety of patterns of mazes or virtual corridors composed of a variety of combinations of textures. Once the meta-policy is applied to the specific tasks or environments during testing, it is able to adjust its weight values using merely 2 to 3 gradient steps to obtain an optimal policy adapted to the specifications. The functions that allows the meta-policy to converge to such specified policies are called meta-learners. As mentioned before, meta-policies are designed to be able to adapt to specific tasks in a few gradient steps and converge to a task-specific policy that output action sequences that attempt to maximize the return for that specific task. In the paper in question, the number of gradient steps it takes to converge is called hitting time. And since meta-policies are generalized to various tasks, there are many task-specified policies that they can converge to, resulting in multiple hitting times, each corresponding to a task-specified policy. The expected value of all hitting times for all such task-specified policies is called regret, which can be used for calculation of performance of the meta-learner F for the meta-policy in question. The optimal meta-learner F** can be defined as the meta-learner that can converge to task-specific policies with the least regret. In order to understand how meta-learning can be combined with skill discovery, it is important to talk about task distributions. To directly quote from the paper, we will define the task distribution as a mapping from a latent variable z sampled from P of z to a reward function rz of s and a. That is, for each value of random variable z, we have a different reward function rz of s and a. Note that this definition is an alternative interpretation to those we have seen in Diversity is All You Need and DADs, which focused on the effect the skill has on how the environment state alters and the minimization of the mutual information between the state space and the skill space. However, it still serves the purpose of breaking up complex tasks into individual tasks, which was the purpose of research on skill discovery mentioned in Diversity is All You Need. This interpretation of skill discovery as diversity and reward functions, probability of distribution of skills can still be interpreted as conjugate prior to all skills discovered by the meta policy, and it is possible to estimate the return when all tasks are taken into consideration, as seen in the integral below. This would also indicate that the estimated return for a meta-learner that has acquired skills can be estimated using conjugate prior. Now that we have an intuition regarding regret in the context of meta-learning and the interpretation of skill discovery as diversity in the reward function, let us delve into the mathematical definition of regret and optimal unsupervised meta-learner. The regret of a meta-learner is defined by the difference between the return of the optimal meta-learner and that of the meta-learner in question, given a single skill-reward distribution. To define the optimal unsupervised meta-learner, it is necessary to define the worst-case regret for arbitrary meta-learners given a controlled Markov process, otherwise known as state transition dynamics or Markov decision process without the reward variable. The worst-case regret attempts to maximize the regret for the meta-learner by altering the conjugate prior for reward and skill distribution. The optimal unsupervised meta-learner is the meta-learner that maximizes such worst-case regret. In order to calculate the worst-case regret, task distribution must be defined preliminarily as a conjugate prior. The paper provides two lemmas for this. Lemma 1. Let pi be a policy for which rho pi t of s is uniform. Then f pi has lowest worst case regret among learning procedures in f pi. Lemma 2. Mutual information I of st and z is maximized by a task distribution p of sg, which is uniform over goal states. Taking a look at lemma 2, it is easy to see the similarity between this and the latency estimation and conjugate prior for the skill distribution, both derived from the mutual information between the skill space and the state space, where the conjugate prior for the goal states or skill distribution was set as uniform by default. Taking a look at lemma 1, it is possible to use the notion that the skill distribution should be uniform to train the policy. In Diversity is All You Need, a discriminator that predicts the next state given the uniform conjugate prior of skill distribution was used to train itself, and the skill policy while being able to acquire new skills. It is possible to, after discarding the trained skill policy, reuse the trained discriminator to obtain a meta policy. Although it seems redundant to discard a trained skill policy, this can be justified since the input dimension for the meta-learner and the skill policy are different. As mentioned before, the meta-learner's input dimension is reduced since there is no need to input an additional skill vector. For the descriptive example of the unsupervised meta-learning framework, the paper proposes a method that learns the discriminator via Diversity is All You Need, discard the skill policy, and learn the meta policy using MAML. One of the experiments tested with this method was OpenAI Gym's half-cheetah environment, where the goal is to make the cheetah model run as far as possible in a single direction under a certain time limit. The results show a high return compared to the traditional policy grading algorithms such as reinforce, and more complex reinforcement learning algorithms such as Diversity is All You Need. Diversity is All You Need, and papers that stem from it excel in automatic discovery of diverse motor primitives. Similar to principal component analysis, where a system with multiple eigenvalues are separated into multiple eigenvectors, the proposed methods train policies without any given specific tasks or skills, resulting in unsupervised classification of non-singular vectors within the skill space. Additionally, by utilizing deep neural networks' ability to generalize input data, these methods are able to combine all of the motor primitives into one skill policy or meta policy. Despite these contributions and advantages regarding skill discovery, there are difficulties in analyzing such learned skills. Coefficients of black boxes, such as weight values of deep reinforcement learning and deep neural networks, are generalized to the extent that it is difficult to analyze and model their underlying structures and dynamics, leading to difficulties in measuring or counting the number of effective differential motor primitives without sampling thousands of points from the output distribution, or debugging a function without practically retraining it from an initialized weight distribution. In DReCon, we found that classical control like PID and LQR can at the very least produce somewhat predictable trajectories that can be analyzed within the field of dynamical systems, while deep neural networks, while they can lead to unpredictable actions, can be used to tune the outputs of the PID control. As seen in differential policy gradient and its application to inverse kinematics problems, the advantage of deep reinforcement learning is its reward function, where problems that are difficult to manually hard code in classical control theory, in this case collision avoidance, can be easily added within the reward function, and with the help of multitasking, can lead to task completion using multiple limbs concurrently. For diversity is all you need, the generalization and black box of deep neural networks enable automatic diversification of motor primitives that can be difficult to accomplish with classical control, can be accomplished using deep neural networks. However, a statistical analysis of the diversity of such tasks can be extremely vague and difficult. Before we wrap this session up, I would like to comment on topics regarding the nature of deep learning and deep reinforcement learning and their effect on data analysis, scientific modeling, and the future of this field. Data analysis uses methods such as linear regression, principal component analysis, independent component analysis, which has a huge documentation and analysis methods regarding causation, hidden variables, Bayesian analysis, etc. On the other hand, deep learning, being a black box, does not. Hence, the only way to analyze its effectiveness and safety is to apply the methods to various tasks and environments. However, the consequences of applying trained networks to previously unseen environments is questionable, since statistical analysis of such methods is extremely difficult, leading to occasional unpredictable sequences of actions, which can be a major security and management issue during applications that has possibilities of human harm, such as industrial robotics and self-driving cars. Scientific modeling's major purpose is to understand the underlying components using reductionist methods, such as calculating the torque in musculoskeletal models and the effect these muscles have on the torques, and analyze the interaction between the various discovered components and their effects on the overall observable phenomena within the field of complex systems. On the other hand, deep learning merely throws in a black box and looks at the problem as merely an input and output, with not much insight to give about the environment. I cannot help but question the point of deep learning within the understanding of science's attempts to comprehend natural phenomena, such as the physics of a robotic system. In my own interpretation, research and advancements on the field of deep reinforcement learning should focus on dealing with sensor noise and control output disturbances. Modeling uncertain environments, even in the field of dynamical systems, and an augmentation of meta-reinforcement learning and hierarchical reinforcement learning methods with classical control theory. Deep reinforcement learning has major advantage in comprehending and managing noise and disturbances. DReCon manages to combine PD control that tend to have predictable trajectories with deep reinforcement learning in order to deal with disturbances and sensor noise for stabilization. which would make it easier for evaluation of the system if errors were to be found in application. Such development pipelines can have many areas to be explored through further research. Modeling uncertain environmental or task-specific elements such as collision avoidance can be explored more using deep reinforcement learning using its manual settings regarding reward functions. Additionally, although not mentioned in the papers that we have discussed here, modeling chaotic systems such as Lorentz equations may also be categorized within the definition of uncertain environments, since chaotic systems are by definition unpredictable due to its changing nature from recognizable patterns to random trajectories. Perhaps the generalization of such unpredictable systems can be accomplished using deep reinforcement learning to predict the trajectory that such uncertain tasks and environments can take in future time steps. As an attempt to utilize the effectiveness of skill discovery and solve the unreadability of black box algorithms, and taking into consideration on how classical control theory can improve the predictability and analysis of a control system, augmentation of skill discovery algorithms such as diversity is all you need and classical control theory should be explored and taken into consideration. One approach may be to utilize the overall framework of meta-learning and hierarchical learning presented by Diversity is All You Need and its succeeding papers by replacing neural networks with methods present in classical control theory. If a method that allows this is proposed in the future, it may help with the analysis of problems that can be seen in current skill discovery methods, such as counting effective and diverse skills by analyzing the hierarchical or meta policies. Future deep reinforcement learning research should focus on utilizing deep reinforcement learning's ability to model complex environments or tuning outputs of other control schemes and classical control systems' predictability and ease of analysis. Hopefully, more advancements that take such problems into consideration will help deep reinforcement learning evolve from the research stage to the application stage, similar to how image classification using deep learning have evolved in the last decade.